welcome to the 11th episode of, Tyler Makes a Game in Corona. This episode may or may not work. I'm hoping it does. If not, I will have to re-record it. What's currently going on is my internet is wonky, but it seems like my upload speed is good enough. So let's hope it is, and get right into it. So if you've been following along, then you know that we've been working on a game, and the last thing we left off on was we're building maps here. Can add trees and whatnot. Can add enemies, and you can add the player and move the player around. And then when you hit play, you've got these enemies. The yellow ones run vertically, the purple ones run horizontally. The player can go to any location that is either horizontally or vertically directly aligned with them. It stops at borders. What we're going to do today is we're going to fix a couple things about the enemy movement. We're going to slow it down. We're going to fix this. If you look really closely, you can see that it actually steps into the locations it shouldn't before bouncing back. And then we're going to start looking at doing an A-start algorithm to actually move the player to any location that we actually click on the map. So yeah, that's what we're doing today. So again, if you need the code, check it out. It's at github/TylerMakes. The repo is called Bulbasaur, and all of the different steps as we make this are saved as tags, so you can actually clone any given tag and you will get whatever it was for that stream day, so you can actually follow along and see the code as it evolves. You can also see it in the commits. If you look at the commits, they also follow along pretty much with a couple of little additions when I fix something that I messed up. But anyway, yeah. Or you can just go grab the code. Like if you see something you like, just grab the code and pull it into your own projects. Okay, so I left off. I had to cut off a little early. And we didn't have the movement going for the enemies. The things that we had to do that I realized just after I finished the stream, enemies aren't constrained by where they're clicked. So if you click somewhere, we're using this algorithm open to player to know like if locations that it's moving to are actually open, so that it can actually move to those different spaces. And what's happening is that these are all open, but then if you move off of it, I can't click there. Like that's actually clicking this button or whatever. I can't click there, that's clicking off the screen. So for a player, we didn't have to constrain it by the edges. But for an enemy is just going to keep walking, and when it hits here, it's going to try to walk there, which is off the map. So this basically says, like, yeah, if the location that you're trying to go to is less than 1 or greater than the number of columns, this is on the horizontal, then you can't go there because that's off the map. And then we have the same thing for vertical, because that's off the map vertical. So that was the key there. That was one bug. So it would, of course, crash because the enemy would move very quickly to the edge. Like right now, they're going super fast. So that's the thing, is like before we could even really think about what's going on, the player, these enemies, one of them was moving right off the map and then causing an error. Because what happens is this tries to get a location that doesn't exist, and then it throws an error. And then the other thing was that we needed to reflect the character. I believe this had something like self.goingleft equals false. but that's not what we want. What we want is that if we hit a location that we can't go to, so open to player is false, then we want to swap the location so that it starts going the other direction. So if going left is true, we want to change it to false, but if going left is false, we want to change it to true, which is why we need it to just not be whatever it is. So that makes it the opposite. Okay, so you can get rid of that. And now we can start in on this. So what I want to do is find out why these are going off the map. Let's also do this. I'm gonna put these here so that I can see if yeah, so it's doing it horizontally and vertically. So let's find out why. So we're going left. We're gonna subtract one from the location. Oh, and as a note, we have these two different AI strategies. So all those changes that I just mentioned needed to be mirrored here. As you can see, they're all, it's pretty much identical, except vertical. Okay, so the question is, we're going left, we do a location. This one is not accessible. When you check that location, so the question is, why is it saying that this is acceptable when it's not? But it's off by 1. So what that makes me think is that what's happening is that we're checking a different tile that we're actually moving to. So let's see. Oh yeah, let's take a look at how we're moving these. So with the enemies, we call update. Let's go look at the enemy. All right. Update. So it gets its next location. It's that. Okay, here we go. So this might be the problem here. So we get this new location. And let's see. So with our AI strategy, I have an idea. What we're going to do is, instead of going left and right, we're just going to give it a stop, so that the first time that it hits something, it's going to stop. And then that means that we won't do anything else. So return enemy location. Self.enemy.location. Interesting. Well, let's find out what the enemy's location is when we're doing an update. Get next location self. And if it's open to moving there, we're going to set the location to the new location. Update the view to that location. Okay. And it converts that location to a map location. Okay. So the problem could be this convert. Like, let's hope that it's not that. If it were that, then theoretically the player would have the problem as well, where we would run into the side of something and it would run through something. So I don't think it's the convert function. If not self. So what this does is, if self.stop is false, we're going to do not false, which is true. So if it's true and the place is open, we're going to go to the new location. Otherwise, we're not. We're going to do this, which does nothing. It just keeps it where it is. So let's save that and see what happens when we play. Oh yeah, that's annoying. We want to drop a tree here so that we can see it happening. Okay, so that's interesting. So, because we are swapping the next direction, but we're actually telling it not to move. And what I would expect is if stop, then it doesn't matter what happens with this new location because we're not returning it. We're returning its current location. So why is it still moving? So the question is, if I were to give it its own location back, in fact, we could even do that. Let's set stop to true at the start. Save that, play. Ah, see? Okay, so even if it stopped at the very start, like we don't want it to move at all, it's moving. So the question is, why is it moving? And it's going to be this. So we're given a target location, and we're going to pull that location from here. New location. Okay, so we have its current location, and if its current location is less than its target location, we're gonna try this. We're going to look at what its current location is. And we are going to compare that to its target. Yeah, let's find out. Now there are two enemies here, so actually let's get rid of one. We just put lava down. Okay. So it's going back and forth. Okay, so its current is 9.2. And its current is 10.2. Its current is 9.2 and its target is 9.2. Then its current is 10.2. So it is still moving even though its current and target are equivalent. So what I want to know is, why is that? Location I is less than its target location I. But it's not, because it's, oh, you know what? I need to know. I might be mixing these. Actually, no. Current comes before target. So if we look at our current, it's 9.2. Target 9.2. Let's do this. Oh, what am I doing? This needs to be target location, of course. Otherwise, we're not doing anything different. Okay, so there we go. Target location. Save that. Throw in a tree here. Put one over here. Okay. So now, let's take a look at this. It's current, target, current, target. Yeah, they're always the same. Okay, that's exactly what we had before. Okay, so the thing is, its target location is its own location. That's what we'd expect. That is correct. Now let's move through this and find out what's going on. Okay, so is new location, which is its current location, I less than that? No, it's not. Because they're both 9. Is it greater than it? No. Is it less than it? No. Is it greater than it? No. So we check that open to player. Do we screw up open to player? No, this should pulls a new location. Here, we're gonna do this. This is very odd. So we're gonna do new location. Put that out here. And then we're going to see if new location changes down here. And then we're going to see if the location changed before we update our view. This might be slow, but sometimes I like to just run the code rather than beat my head against the wall reading it. Oh yeah, we're just having it go back and forth. Okay, so let's stop that for a moment. Oh, is it not done? That's interesting. Oh, there it goes. Finally, it's done. Okay, let's start here. Current. Okay, now we're getting somewhere. This might be interesting. So its current is 9.2. Its target is 9.2. It's new. Current is 9.2. Now, current is 11.3. How did it get to 11.3? Now its current is 10.2. That's interesting. Oh, you know what? Let's get rid of its... That's why. We've got the two enemies there. That's annoying. Okay, let that run for a little bit. Now we're gonna stop it. Over the bottom here. Okay. Everything is 9.2, then everything becomes 10. Ah, here we go. So, no, everything is 9.2. Then its current becomes 10.2. Where does that change? That is a really interesting bug. How do we get its location? Oh, I have an idea. Let's go to this. It's a little out of order, but that's okay. We're gonna do 3 and 4. Okay, drop in a tree, hit play. Okay, so current. Let's start up here. It's 9. Its target is 9. New current 3. It's all 9. And then the very next round, its current is 10. Even though we didn't do anything to it. Oh, here we go. Maybe we are missing it up here. Oh, you know what? I think, oh, you know what? I think it's this right here. I can almost guarantee it. But we'll see it right now in the code. So here we go. Let's hit play. Let it go for a little bit. Finish. So now if we go look at this, what happened? So the first one is actually current 5. And then 6. Okay, so looking at current 5, it's 9. And then before 6, it's 10. Okay, so between here it's 5, and here it's all of a sudden 10. So now we know that our AI strategy, get next location, is changing its location. Why is that happening? Well, the reason is that is the concept of passing by reference or passing by value. So what happens here is that, let me make sure I'm not dropping in bad code. Okay. What's happening here is that here we are calling a method, AI strategy, and we're passing this object self, which is this enemy. That's great. we want to get its location, which we're using here. Now, its location is an object, remember. It's this. It's got I, whatever, and J, whatever. What's the problem that we're having is that because this self is this enemy, right? Like, this is, we're getting its location. When we alter it, when we do this, we are altering the enemy's location. So then when we return it, we're returning a version that has been changed. So in order for it not to change, in order for this to actually just be the new location, what we have to do is this, which you'll notice we were doing before, and I didn't really explain why we have to do it, but here, you have to get the location again and create a brand new object. Now, the numbers themselves are just numbers. Those are just data, and they're not connected to anything. So each instance of those is different, whereas the actual object, the enemy location object, is not a different instance. So we have to make a new one. I hope I'm explaining that well enough. If you don't get it, the concept is passing by reference or passing by value. And if you look that up, there you'll probably find a much better explanation of that concept. So let's go ahead and do that. And actually, let's copy that over to our other enemy. Oh wait, AI strategy here. There we go. Let's save. Let's run it. Oop. What was the problem here? Oh, duh. Should be, of course, I. And this should be, of course, J. There we go. Now we're going to copy that. Go here. Paste it. There we go. Hit play. Okay, now you can see it's bouncing within. Now the purple is not moving because we added this stop. So let's get rid of the stop. And there we go. Now we have things moving as we expect them to. If we go back and we throw in a couple of trees here, we'll see that it bounces nicely between the trees and does not go stand on the trees. Okay, cool. So now the next thing is they're moving really fast. So we're going to make them move a little slower. So what we really want is actually to animate between these two things over a course of frames. What do you think about that? So we want to animate everything, and that's a different kind of update. So there's like an animation update, then there's a regular update. Actually, let's not deal with that right now. We'll leave this as it is. They're moving fast. I have to think about how I want to tackle that, and we'll come back to that in a little bit. For right now, what I want to do is jump into the A-star algorithm and try to figure out how we're going to make our player walk anywhere on the map. And to do that, we're going to follow extremely helpful tutorial on an introduction to A-star algorithm here at Red Blob Games. So, you know, any good programmer will rely on the resources out there, and if you just Googled like AI pathing algorithm, I bet that site is going to come up. Well, it might only come up because I've looked for it, but you might see like here A-star is one of the first things that comes up. And then let's say we were going to go implement A-star algorithm. And hey, look, this is one of the first things on there. Interesting. Yeah, there's probably a bunch of other awesome resources. You can even look for your particular language. Let's see if somebody has actually implemented one in Lua. Hey, look, here's an A-star Lua. Clean, simple implementation. Usage. I don't want to look at usage. We want to look at the actual code. Blah, blah, blah. Yeah, I'm kind of curious like how they've set up their graph. Actually, let's look at the usage. So, which namers are valid, within range, A-star distance, start, end, all nodes. Yeah, here, you gotta send them all nodes. Yeah, it's maybe a little different from ordering. Anyway, so what I really like about this site is that this guy writes all these tutorials but makes interactive animations that teach you how they work. This is basically something that you should go and read, and then, you know, pause the video, go read this, come back, I'll wait. Just, you know, go and read it, come back. Okay, hopefully you've read it now. Pause the video, came back, read it. Now we're gonna go through it. So this is what we want, and I'm probably gonna add this. So I hadn't even thought about this, but it's a cool thing. So if you look at the way his stuff worked, is that the distance between water, like these count for 10 times the distance of like walking through something else. So if you move it here just one thing over, it's quicker to go around the water. If you go through here, it's quicker to go through the water. So that's a little nifty thing. So A-star starts with the breadth first search. Breadth first is a method of going out like the breadth of something. So if you had like, let's say you had your star right here. The options to go out breadth are here and here next to it, right? Depth first is a different kind of thing that you use in other scenarios. And depth would be like, let's say we were trying to get to this location or something. Depth first would be to go all the way, like start here and keep going deeper, 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 deeper until you hit it. And then back up here, start on the next path and go deeper, 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 deeper until you hit it. Because of, you know, so the way this algorithm works is that you start by going depth. So you go out in all directions at once, and you keep going out in all directions and all directions and all directions as you go. So that's what breadth first is. And you can see these, he has these cool animations, or not animations, art that just shows like contour lines that kind of give you the concept of like what's going on here. Like they're all a given distance. I prefer these that actually show close up. Like this close up shows you what's going on. Here, we're gonna go back a few steps. So here you go. So first we're gonna go to this block and above it. So actually, this is not explained yet, but all the adjacent cells are numbered here, right? 1, 2, 3, 4. That's the first step. Then the second step is, hey, look, we're going to start with the first one of these adjacent cells, and we're going to go to every adjacent cell to it. Actually, let's move it down here. So here we go. So here's the first one. See, 1, 2, 3, 4. Now we're going to go to every adjacent cell to it, and see, so those are 5, 6, and 7. And then we're going to go to 2 and go to every adjacent cell. These 2 are already visited, which is why we get only this one becomes 8. And then here's 3. You know, these 2 are already visited, so this will become 9 and 10, and so on and so on, until they're all filled. So what we have to do is this. So he has this concept of the frontier, which is the blue area. It's the right here we pick our frontier, which is all the adjacent tiles. Now that we've got our frontier, we're going to go through each block in our frontier and make a new frontier, and take the block and add it to the visited squares. So we're going to start with that. So we have our frontier, which is a queue. In this case, it could be a list. It's whatever kind of list you need. So in our case, we're going to use arrays because that's what we have. Then we are going to put, in this case, they're putting the start location, which is this location, into the queue. That's how we start it, is right here. This is our queue, is just the one. This is Python, by the way, if you noticed. Okay, so putting that puts it in the queue. We're going to go through this in Lua, so you'll see how that works. But I just want to show what he's doing here. So visited is empty. There's no visited. Then what they do is immediately start the visited start. That's this first one is set to true because we've already visited. Now, while the frontier is not empty, so we have this queue which has all these elements in it. We're going to get one of the elements from it, and then for next in graph neighbors. Oh yeah, so what we do is we're going to get all of the neighbors of the current location. So in this case, like we start with start, we're going to get all the neighbors, which is those 4 tiles around it, and then we're going to step through each one. And if it's not in visited, as in it's not already been visited, then we're going to put it in visited. Or I mean, we're going to put it in the frontier. And then we're going to visit the next, or yeah, now we're going to add it to the visited list. Sorry. So if it's not visited, put it into our frontier, and then set it visited. Now, interesting. So this doesn't. Oh yeah. So neighbors. This neighbors function. This is what tells you which ones are actually open. This is kind of like our open to player. If you gave it a list of places, or actually you gave it a location, you said, give me all of its open neighbors. So yeah, if we are here, like actually, yeah, there we go. When you say get neighbors of this square, it's going to give you these 3, which will light up in blue, right? Like those 3, because this one is not a neighbor. It's a blocked space. But if it were a neighbor, it would be in the list. So there we go. So that's the basis first, is to get that. Now what I'm wondering, oh yeah, so in order to do just the most basic pathing, you just put a location from where it came from. It basically tells us how to, it doesn't construct a path, it only tells us how to visit every place on the map. Because it's just flooding out to everything and saying like, okay, how, or can I get to this? And like he says, you can use it, it can be useful for distance maps, procedural map generation, and lots of other things. But we want to find paths. So what we want to do is keep track of where we came from in order to have actual paths. So as you can see, when this goes out, you're here, this tile came from that tile, and this tile came from that tile, and that tile came from that tile, and that way, when you go out here, you can actually path to any of these locations based on just saying like, okay, is it a place that's visited, which means we can get to it by the time we've, flooded the entire thing. And then, like, finding the paths back to here. What I want to know, actually, is if we did this. What I'm thinking is, I guess you can't. See, what I want to know is what his code is doing when you select this guy. because he's obviously got code to do something so that it doesn't break when you can't reach a location. But he didn't include any of that in here, it doesn't seem. Anyway, that's fine. That is not what we were worried about. So we're going to start by building this. And this just, you keep, the only difference is instead of visited, it's where they came from. And this is none. Instead, when you look in came from, you set the current location as the place that it came from. Okay, so current is a location, which is in our list. Okay, so got that? I hope you got that. Now we're gonna start figuring out how to do that. So for this, I'm gonna go ahead and make a new file called A*, bulb A*. Well, give my machine a little moment to work. Let's go bulb A*. Okay. As always, we're going to use our just basic class construction. Call this A* pathing. Call this bulb A*. This isn't going to have any values to keep track of. We're simply going to do something like this. So what we want to do is we really just need this. And go get path. We're going to go start. And there we go. That should be the basis of what we need. Now let's go take a look at this algorithm. We're going to put it right here. And then we are going to basically do the same thing here. Okay, so let's actually, might as well do this. We're going to set our initial values. Frontier. Let's actually do this. We're going to go reset. Our frontier is just going to be an empty list to start. That's what we need. Okay, and so we're going to reset just to make sure everything's great. Okay, now what we're going to do is we're going to put start in our frontier. So what we're going to do is frontier, the length of frontier, +1 equals start. I really hope that I'm able to accomplish this. We'll see. I haven't tried this before. So if it doesn't work out, you're going to get an experience of like some good old-fashioned debugging. So I hope you're prepared. Okay, so came from, which actually, you know, we're going to go ahead and just put that in our, and this one should be self, and this one should be C. Start everything off blank, as we do. So we're going to put that in start, and then we're also going to go. Now this is a little different. Came from is a hash. It is not a queue. So instead of adding it like this, where the index is the number, the next number, came from is going to have the start location. Right? And what do we want to do for that? For right now, we're going to put none in there, kind of like they do. don't yet know what we want to do with that. Okay, so wow. Oh yeah, let's do a. Sure, we can do the same kind of while loop. Yeah, while A, do that. What I want to see is so. Sorry if you can hear the fire alarms in the back. What I'm curious about is if we move. While iterating. Yeah, that's what we want. Okay, so we're going to do something similar to this. This is what I usually do. So the idea is that let's take a look at his algorithm. Actually, let me get rid of these other files. Okay, so while this is not empty, so what's happening is while there are elements in here, he's getting the last one and then doing this stuff, right? But yeah, so we can do that here. That should work. So we're gonna go while while that frontier has any elements in it. Now what we need to do is remove that element. Let's go look at this. I think it's Lua's table remove is, oh, I don't like how they put this in one page. Table remove function removes and returns an element from given position in an array, moving down other elements to close space. That's fine because we're actually going to go from the end of the array. When it's called, oh, here, this is nice. When it's called without a position, it removes the last element in the array. That's exactly what we want. That's the same thing that is get is doing. So we're going to do that. So frontier dot remove. Oh wait, you know what? I think it, the way this is written is table dot remove. Frontier. Yeah, see, A is the table. Yeah, it's the same kind of thing where it's table dot remove and then the name of the table and then the number. Okay, so we remove that guy. Now we need to get the neighbors. So this is a for each. Oh no, that's not. The for each in Lua, I think, is pairs. Yeah, 4K in pairs. Or this is key, or there's like index and value. Is that? Yeah. So we want index and value. So pairs. Oh wait, keys of a table. Okay, so we have an array A. Oh, there's I pairs. Okay, that's what it is. That'll give us an index and value. We really only care about a value. But anyway, so we have an array that we need to get. So we're gonna do our map. Get neighbors given our location, which is going to be current. Okay, so we're gonna have to implement this get neighbors, which we're gonna do in a second. I'm gonna go ahead and finish this. So what you need to know is that these pairs are going to be, there's just gonna be an array of different neighboring points in the map. So it'll end up looking like something like this, where it's I1, J1, and then you might have like this, where it's -1, and this one's -1, and then they're both -1. Okay, so this is where, like, at location 0, these would be the locations around it. Oh wait, no, that's not right. This would be at location, no, what it should be is zeros. Oop. 1, 0. Wait, let me think about this. We're in 0. Above it, 1, 0. Oh yeah, that's right. -1, 0, 0, -1, and then 0, 1. There we go. So we go from 0, we go up in this direction, or like this is horizontal, so 0 and then 1 is to the right, 0, -1 is to the left, 0, -1 is up, 0, 1 is down. So that's what it's going to look like. It's going to be the 4 locations around a grid square, which is the same thing that his does here. So it's these are our locations. Imagine this is 0. This is 0, 0. This is like this is 1, 0. This is -1, 0. This is 0, -1. This is 0, 1. So that's what we have. Okay, so now we have all those. That's great. Now, what we're going to have to do, and this is going to be interesting. So, given I, actually value, that's what we want, is the value. It's not in. Okay, so what it means to be in came from is that this this object, the equivalent of this object is in there. So if v is, so we're gonna go not in self in came from. So we're gonna make a function to say like, hey, this is in came from. Then we're gonna do this. Oh. So this is what that's gonna look like. Let me think about something. We're just going to be adding these locations to came from. And all of these locations have an I and a J, which is their given location. I have an idea. We're going to do this instead. We're going to make our came from a graph itself. So what we're going to do is go insert into came from. And so given a location. Ooh, I can't type. Let me think. Oh yeah, so that'll be fine. Okay, so came from, it's just an array. So what we do is this. If came from dot, or no, if came from location dot I. So we're gonna go if not. So if location I does not exist in self dot came from, then self dot came from location I equals a new array. Then what we do is go self dot came from we're gonna do value here. Self dot came from. Now we're gonna go location I. That's our initial one. We're gonna go location dot j. That's our second place. And then we're gonna go equals value. So we're gonna put that value in came from. So instead of doing this, what we're gonna do is going to call insert into came from with start and none. So came from at start location, this is the ID, and then this is the value, and those are going to be put into this nice hash array. And so then we can say, instead of this, we can actually do if not, let me think. Yeah, if not came from. So this would say that, oh wait, here. We're using v. That's getting a little confusing. So we're gonna put value as next. Let's go next neighbor. I didn't want to use next because if you see next is blue because it's a keyword. We don't want to use keywords because that could do something else. So if not, I'm going to put parentheses around this because I prefer parentheses. Make sure we know what we're saying. If not came from next neighbor dot I or not self dot came from neighbor dot I next neighbor dot j. So what's happening here is that we are trying to say, all right, if came from doesn't even have an I list, then don't even bother looking for ij. If it does have it, then we're going to test that. But if that doesn't exist, then we know that it's not in there at all. Okay, so that's this. It's not in came from. So if it's not in came from, then we want to add it to the frontier. Ooh, interesting. So he's using a queue actually. So the queue means that the first in is first out. Trying to think if it's better to insert at the front or remove from the end. It actually doesn't matter either way. We just want to make sure that first in is first out. And what this would do is let me think. So our frontier, get the current. If we have like say 4, we're gonna insert these. See, this is gonna remove it from frontier. It's gonna insert these into frontier. And so we're going through the first one. Yeah, what we actually want to do is we want to remove first element. That way, the first thing in is the first thing out. And I bet, like, let's go Python Q get. There's a lot more stuff than I care about. Just want to look at get. Blah, blah, blah. I was hoping it would tell us where the element comes from. is more complicated about locking and everything. Just want this simple queue explanation. Yeah, it's like talking about multi-threaded programming, etc., etc. That's not what we actually care about. Anyway, we're not going to worry about it. I'm pretty sure this is when elements. The idea is that if we had frontier, and let's say we have frontier, and at first it's just start, right? It's an array, and the first thing in it is start. Then when we go through this, we're going to add 1, 2, 3, and 4. Then we're going to, oh, actually, sorry, we're going to remove start, and then we're going to add 1, 2, 3, 4. Now we're going to remove 1, right? Or let's say what our code before did when we were going from the end is it would remove the last thing in the array. It would remove 4, right? Well, then we're going to add 5, 6, 7, which are all the neighbors of 4. And then we would take off 7. That's depth first search. Like we're going continually deeper and we're not checking these things. So instead what we want is to not take the last element, we want to take the first element. So what we do is we take off 1, and then we go and we're going to add 5, 6, and 7, which are the neighbors of 1. Then we want to take off 2, check that, and then so on and so on. So that is why we want to take out the first element of frontier as we go. Okay, so there we go. We've got that. So now this can be simple. It's just we're going to copy our code from here because it's a lot of junk to type. We're going to go add it to the end of frontier. Next neighbor. And self dot. Yes, we want to insert into came from our new neighbor. We want to set the value to current. And that matches this code. So there we go. That should be, I comment that out. That should be our version of this. And by this I mean this. Okay, so I'm going to go ahead and save that. Now let's go find out if this even remotely worked. So what I'm thinking about is, okay, so let's say we go ahead and do this. Now, given a location, we are going to want to find that location in this, which is actually going to be easier because it's going to have our whole came from. And then we're good to go. So yeah, okay. Okay, so the next thing we need to do is our get neighbors. So let's go ahead and do that real quick. So given our forest map, we need a function called get neighbors. Neighbors. So actually just thinking it would be good to copy and paste just to make sure that I'm not spelling this differently. I mean, ideally, you spell correctly every time, and but if you're not going to spell correctly, at least make sure that you're consistent. Okay, so let's go location. And we want to get neighbors. So what we do to get neighbors is say, in this case, we just want to say, we're going to go like around the clock. I'm trying to think if there's a nice way to, let me see something. Never mind. We're just going to do this a simple way. So, going to go around it and say Okay, for... no, I think we're just gonna have to do this individually. So what we're gonna have to do is go, all right, we are going to say new location left. There's other like nicer ways. For instance, we could actually keep track when we actually build our map. We can have every location keep track of all of its neighbors. That might be good. That way you can actually do some cooler stuff, like have neighbors that are not bi-directional, where this, like say, this square right here could have this as a neighbor, but this square will not have this as a neighbor, which would then mean you can only go through it in one direction. Right now, I'm just going to say like, hey, if I have this location, check this one and this one and this one and this one. And if these locations are open, then they are going on my neighbors list. You can get fancier stuff later, like I said, where you say like, you know, this has this neighbor, but it doesn't have it the other way. But that's not what we're going to do for right now. So we're going to go with the location left, and we're just going to go, we're going to make our new location. This one. We're going to go ahead and do each of our locations like this. Left, right, up, down. Okay, so this is right. This one's up. This one's down. And as you may have noticed, I didn't put in code here that should be here. There we go. Okay, now we're actually going to do something fancy. We're going to say new locations equals this. Actually, I'm going to move that up. And we're just going to do this. Locations. We're going to put each of these in this, in a, well, actually it's a hash. It's equivalent, like, actually, you know what, let's just make it an array. This is our, actually, if we want to get really simple, this is what we want. Which we've done this before, so it should be familiar to you if you've been following along. But the idea is that we're just adding it to the next location in our array. And if we just do that 4 times, you know, the location gets incremented because we added something to it, and we just add those to it, right? So that's all nice. We're gonna, I just want to have these here so we can know what these locations are if we decide to go and change it later. The reason I did this is because now what we want to do is go for okay. Actually, let's see. Ooh, I want to know, because there's like several different ways of doing it. Yeah, see, we can do name and I pairs. Actually, yeah, let's just do a normal loop like we're used to. Do they actually do local? They don't. Okay. So I equals 1. And then we're going to go to the length of new locations. We're going to do this. And we're going to say if self open to player new locations I then neighbors. Here's our new neighbors list. We're gonna go neighbors. This is our array, so we're gonna do the same thing. Equals new locations I. And then we are going to return neighbors. There we go. All right, let's hope that all this stuff worked out. So yeah, just remember. So this is just making an array that has each of the neighboring locations. And what this does is it says like, hey, let me check each of those and make sure that they're on the map. That's what this part does, and that they are walkable. Yeah, see, return goal.walkable. And there we go. And then that's our neighbors. And then we've got our A-star algorithm. So what we want to do is when you click a location, this is where we are updating the player location. No. Wait, is it the forest? It should be the forest, right? Right. Yes, player set target location. That's what we want. Okay, so let's go look at the player set target location. Player. Basically, when we set target location, for now, we're going to imagine that all of them are acceptable target locations. We're going to actually just, you know, allow it to set it as a target location, but we're also going to give it a path so that it can follow the path whenever you do this. So let's figure that out, though. Player location. Set target location. Okay, it's trying to go to that location. Great. Now, what I'm trying to think about. Okay. Yeah, so this is going to insert all these things into came from, right? All these new locations. Now, what we're going to do is we're going to say, we're going to add this new thing. We're going to go, actually, no, we don't need to do it there. Okay, so once next neighbor, see, we were going to insert next neighbor into current, came from or whatever. Sorry. We're going to insert next neighbor with current into this. Now, when next neighbor, if, and let's see, we're going to need a goal here, just to start. So if next neighbor dot I equals goal dot I and next neighbor dot j equals goal dot j. So that means that we found the goal. Then we are going to return something. We are going to return came from, right? That's what we want. And when we return, that's going to stop all these loops. This is all just going to end. It's not going to keep going. We're going to return came from. And why are we returning came from? That's because that is going to tell us. That's going to tell us all we need to know to path to it. So let me think about this. Here we go. I know what we're going to do. We're going to do self dot. We're going to do get path. Okay, so what we actually need is we're going to need a function that's going to return the actual path. Oop, nope. We can't call it get path. Let's go get actual path. So what this function does is it figures out all of these locations, right? Like it figures out this, like how to get to every single one of these different locations. What we want though is we actually just want the one location. Oh yeah, here's a good example. So it goes and figures out all these arrows. We don't care about all those arrows. We just want this one. And actually, this is what we want, is this early exit, right? Like this is the equivalent where we're spreading out. But once we found the location, we don't need to keep going and finding out all these. We just stop. So, you know, if, oh yeah, I guess you could do it that way, if current equals goal. But what he's doing is he's saying that like, hey, if we figured it out, then stop. And actually his is not as good as ours is going to be, right? Because he's saying if the current is the goal, that's why you have all these nice angles around here, right? Like if you look at his, you know, it has this nice angle along this whole line, right? Because it goes out in all the directions. However, ours, let's say it's right here. And let's say we went out, and then we got to this point. And actually, you might be able to see it better if we do it on this map. So let's say our goal is right here. We're going out. When we find that location, I'm going to get rid of all these so we can see this even better. If we are starting, oh, actually, you know what? This is the one to do it from. Okay, so let's say our location is here. So here we go. So we're adding all the locations to the sides, blah, blah, blah. Now, here we go. Here, our next includes this. When we go to the next, it's going to be the sides of 10, right? So this is the point, actually, where, oh, nope, 9. Yeah, it's just doing 9 first. That's annoying. Okay, let's say that our grid was this location right here. Let's say that was our goal. This is one of the next locations. If this next location is our goal, then why bother checking this? Or like, you don't even have to check these either, but let's say we already got this list. We check here, right? We don't have to check anything else around it. So we can go, we don't have to get the next for this one and this one and this one and this one and this one stuff. So it's just a little bit simpler, maybe, unless I'm missing something about the order in which this is happening, which is entirely possible. But I don't think so, unless this queue has, I'm trying to remember, this is why I wanted to look it up, unless this queue that he's got puts things in from the bottom and gets them from the top, in which case it'll be the same thing as ours. But anyway, that's something to think about. If you know more about algorithms, you'll know what I'm talking about. It's not that really that important. Anyway, so follow the arrows. So if current is goal, yeah, while current does not equal start. So this right here, this is the algorithm that we are going to create right here to get the actual path. So given the current is the goal, then what we do is we start making our path, and while current does not equal start, what we do is update current to the last element. Get the came from current, append it to the path, and then reverse. You'll see it. It's easier to explain in Lua. So here we go. So we know that we've already added next neighbor, right? We've inserted it into came from. But here, so we're gonna go next neighbor. And So next neighbor is the goal. And then we also want the start. Like, so what we've determined here is that next neighbor and goal are identical. We could actually put start, goal, but I think next neighbor is a little more, makes it a little more apparent as to what's going on. So we're gonna go start, and this is gonna be goal. And what we're gonna do is we're gonna go path. It's our new array of path. We're gonna do the same thing that he did, which is while we have a little more complicated because we can't just say nice equals unless we actually made these into tile objects that have an equals function. That's beyond the scope of what I want to do. So what we're going to say is if, oh yes, we have to say current equals goal. So we're at the end. So if current.I is not equal to start.I, or current.j is not equal to start.j, that means we haven't gone through the entire thing in reverse yet. Then what we do is we say oh yes, I think the way that he's doing it, yeah, we're gonna do this hashtag path +1 equals current. So we're gonna have it added on there, and then if the current is not the goal, like if we're not already there, then what we have to do is we have to add currents came from, which is the way we do that is go self dot came from. Oh, where are we still? Oh, that's just down here. Okay. Self dot came from current dot I current dot j. Because remember, came from is a hash where each of these, the I and the j, are the lead us to the status of what the current is. That's how our insert works, right? It puts it into the ij. Okay, so equals ij. That's great. And then yes, we just, oh yes, so it's goal, blah 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 blah. Oh, and then yeah, so this is, so now we've put them all in, but we've put them in from goal all the way to start, right? So he reverses it. I wonder if there's a helper method we're going to reverse it. If not, we're just going to traverse our table the other way. It's whatever. It's not a big deal. Like, yeah, I don't want to have to add a function just to reverse a table. Oh, that's interesting. Yeah, that's fine. We're not doing that. Sorry, just want to check something. Okay, so yeah, we're not going to reverse, and the reason we're not going to reverse is because it's just as easy to traverse our path from the end. So you just have to know that our path is in reverse, which is fine. We're going to put that here. Okay. So we have all this code that we haven't tested, but we're gonna just cross our fingers and hope it works. So what's gonna happen is when we set a target location, we've got this location, right? And then what we have is we have our our update. On our update function, we get our new location, right? And we check if it's a location, blah, 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 right? There's something cool about this, right? It's like, so this open to player, this makes sure a place is open to player. So what we're going to do is I'm going to set the target location to whatever it is. And then we're also going to set the path. We're going to find the path and we're going to set the path. And then on updates, we're just going to go to the path. Like, we don't actually have to do this check. However, later we might add this check back in, because what we want is the player to keep moving towards a location, but if all of a sudden something in the map changes and blocks it and cuts it off from one of those locations, then what we want to do is say, oh, nope, you're stuck. Stay where you are. Don't move. But we're gonna go look at that later. First, we just have to build our path. So all we have to do is this. The player has a reference to the map. That's great. So when we set a target location, right here, sorry, I keep moving this up. What we're gonna do, oh yes, and if it's, so let's say it never hit this, right? They never equal each other. For this loop finishes, self frontier is no longer anything. Then what we're going to do is we're going to return false. And that'll let us know that, hey, this did not work out. Actually, let's return nil, because this is an object. Let's think of it as an object. Okay, so we have a target location. Equals of NX. Oh, this was our limiting it to horizontal movement. We don't have to do that anymore. So we're going to go like this. And now what we're going to do, we're going to go path equals map get path player. Do we keep track of the player's location? Player start location. Yes, player location. We are updating it. Okay, cool. So what we're going to do is player location is our start. Our goal is this. This is our target location. Okay. That's our goal. And then, oh yes, we need, get path is not on the map. This is self.map. We want to pass that to it. What we want is a star. Oh yeah, so we're gonna create an instance of a star for us to use. Let's just do it here. Let's keep it in the player. And like I said, it doesn't have anything, no parameters. Gotta make sure we require it. Oh wait, that's not how you do that. Yeah, there we go. And no, we've got it and access to it. So this should be a star. Great. Now what we want to do is this. Say if path, which like I said, it'll return nil if we don't have anything. Otherwise, it'll return this nifty path that we found. Then what we do is set the target location to the target location. That's actually not useful anymore. We're actually, what we care about is do path else, and we're going to call this reverse path, so we remember that it's in reverse. Could not path to location. Okay, great. So now We're gonna go up here, do player reverse path equals nil. Yeah, we might tweak this around a little bit, but for right now, I'm not gonna worry about it. So instead of getting this, what we're gonna do here, instead of our old movement, is just say local new location equals health dot player reverse path, and we want to get the last element in it, so we're gonna go self dot player reverse path. So that's the last element. Let's go ahead length, and that's going to set the new location. What I'm thinking about is it's going to go ahead and update the view, blah, blah, blah. Actually, what we want to do is we're going to use table dot remove, because we want to get the last element in reverse path, and we actually want to remove it from reverse path, so it's no longer there. We need to do this to make sure that there's even a reverse path to do this to. Okay, got it. If it's open to that, blah, blah, blah. And let's make sure that it's got. Why is this not auto-completing? Okay. The length of it is greater than equal to 1. That makes sure that it's an object, so we have a path, and that the path has a location in it. If that's the case, then we check if that location's open, set the new location, then go ahead and move. Okay, so let's save it. All right, let's see if any of this worked at all. Never bank on your first try. All right. All right. What did we mess up? Let's find out. A star line 11. Attempt to index local self. A nil value. Line 11. Restart. Oh, that's because we didn't do this in our reset method. Okay. It's great. It's a nice, easy one. A little softball. All right, line 29. Bad argument to remove. Table expected. Got nil. Bulb A star. 29. Frontier. Ah, this needs to be self.frontier. Okay, another softball for you. Okay. Now we're getting into the juicy ones, I think. Attempt index value. No, maybe not. 16. Came from a nil value. That is kind of the point. Attempt index value came from a nil value. Huh. What I want to do is say just make sure okay, let's see what's happening there. I'm wondering if this is happening on our first playthrough. There's no way to know until we do this. Okay. Okay, so value is none, and there's a table there, right? So that's great. Now, value is nil, and the table is nil. So now we're doing something wrong. Ah, here we go. Thought that might be what it was. Again, gotta do the colon, otherwise it's not launching from the right context. Okay, there was a lot of stuff going on. Oh, maybe it's gonna crash. This probably means our loop is bad. Okay, so we've got a problem. We're gonna have to just wait for this to crash. First, let's get rid of these. And what we're gonna do is a couple things to make sure that this doesn't explode. So run times rail. Okay, so I'm gonna parentheses here because that makes me feel more comfortable to see those wrapped together. So what we're gonna do is we're gonna make a run times, which is the number of times that we've run this or through this loop. And the reason for that is because like right now it's gonna be very hard to tell like what we did wrong. But if we increment this run times value, this will stop everything once we have hit 100 times. And that way it'll just loop 100 times and it'll crash, and then we won't have it beach ball like this, and we don't have to deal with that. We're actually gonna have to force quit this, I bet. Force quit, sorry. Because we don't want it to run forever. Okay, so this should not run forever. It should only be the while loop. That is the danger of while loops. Oh wow, that is really annoying. So yeah, we're gonna make sure that it stops after 100 times, and then it just returns nil, and then maybe it'll explode, but at least it will explode in a nice way. I'm just trying to make sure we don't have any other loops that we're gonna have to worry about. Or get neighbors doesn't have any. Yeah, it's just got a simple for loop. That should be fine. So yeah, it's got to be that while loop. If the while loop is breaking, it means that we're doing something like this might be wrong. I don't know. Let's do this. Let's get the length of the frontier. And let's go. There we go. That should give us a clue as to what's happening. Let's find out. Okay. All right, we got about 20 minutes. Let's see if we can figure this guy out. Okay, play. Boom. I should have printed the count. That would have been helpful. Just to make sure that we're actually doing this correctly. Oh man. Should not be and. Or it should be and this should be less than 100. That was dumb. And this is why I should have printed it out. Alright, we gotta force quit it again. Close this guy. Open it again. Always be careful with your while loops. If you're doing a while loop like the one we're doing here, which does a lot of complicated stuff, it would behoove you to actually test it first. Do something like I've just shown you, where you add a break to stop it from happening more than 100 times. let's grab that one in. Self.runtime is less than 100. We are not resetting within this. Should only happen 100 times. Don't get why it's crashing. Let's take a look at this. Trying to go to 13.6. Yeah, see, we're doing 10, 9, 11, 10, 10, 8, 9, 8. So if we're here, 10, 8, 9, 8. No, that doesn't look right. Our locations. Yeah, I'm just gonna let this hang out for a bit while we figure this out. Let's take a look. So, trying to go to 13.6. From current is 10.8. That's great. The first place that we go is 10.8, so this should be 10.8, right? Oh, okay, good. Yeah, so then we go 9.8, go 11.8, go 10.7, 10.9. That's great. Didn't find it. Now what we do is we go to 8.8. Now why is that? So we're going to go 9.8, and we're going to check 8.8, which is this one. Huh. I'm also wondering why it's crashing. Now what I'm curious about is it might be crashing because we're hitting some kind of size limit. But I just don't think that's the case. I think something else is going wrong. Would like to know precisely where it's dying. I have a couple interesting ideas. First, let's see, open to player. We're gonna take this location. Oh, what is it? It's got a tile info. I want to see something is when we click, we place a tile, right? We have a tile. Yes, this is a tile. Okay, so what I want to do is, all right, if it's open to the player, what I want to do is I'm going to do something crazy. Take our new location. Oh, wait a minute. What's going on here? New location's I. That's fine. Okay. And we're going to do something a little weird in that we're going to change the tile's color. Forest tile. I should get moving. Actually, you know what? I don't even care about the parameters. We're gonna set the tiles to black when they're checked to see if they're a neighbor. Where did we go with that? Okay, here we go. IJ, we're gonna go to that one. And we're gonna go set color. Okay. we're going to see, this might help us in that it might tell us where this is happening. I actually could have just figured this out by looking at what the last location was, the one where it crashed, but whatever. We're going to figure it out. Okay, so play. Click. Ah, something's wrong. Line 35. Oh, yeah, of course. It actually occurs to me that it might die when the location is hit. Oh, it's not even going to update because we're not even making it into another loop. That's annoying. Okay, well, whatever. Okay, so our goal is 13.5. It dies 14.9. Okay, what's interesting about 14.9? 1, 2, 3. Okay, wait, this is 10. Our very first current is 10, so this is 10.8. 11, 12, 13, 14, 9 is right here. It's interesting, and then it's next to a barrier. All right, I'm not sure. We're just gonna brute force it. I want to figure out what's going on. Okay, so what we want to do is see something here. So current, let's go print neighbors. Or actually, let's just go like this. We're gonna see what the next neighbor is. I think if we do, hopefully this, we'll do a tab. And then we're gonna do next neighbor.i, next neighbor.j. That's great. What I want to do is tell us that we're adding it, and what we want to do is say what self.frontier's length is. Why? Because, like I said, if something's going wrong, where we're like maybe we're exceeding the possible length of the frontier, that's how we're going to find that out. If we are doing that, that could make this fairly interesting to try to work around. But I wouldn't expect it. I would expect it to have like a normal crash. Okay, there we go. Neighbor 127. Yeah, this is 12.7.12. Should put comma here. That's annoying. Okay, and it's adding to. It's only got 8 in it. And the neighbor it's adding is 13.6. It's 13.6. Okay, so it's not our neighbor. Just make sure we're not doing that. Let's see. Ah, dang it. It's going to tell us that we're making a new I. This is tell us j, and it's going to tell us value dot I, value dot j, so we know what we're putting in there. Shit. I can't think of why this might happen. Well, let's put in I here just so that we can see what I is. Maybe that's causing an issue. I also want to see what runtimes is. I really hate having to force quit programs, like one of my biggest pet peeves. Alright, can we figure this out in the next 10 minutes? That is the goal. Play. Click. And where do we crash? Hey, we crashed when we found it. Okay, so that's curious. So maybe our A star is working just fine. It's actually our player that is screwing up. That would be amazing to me if it was just one of these dumb things. Something dumb that we did here and not the A star. If the A star works great, that would be amazing. If path. That's interesting. Okay, we're gonna force code this guy. Hopefully this is gonna give us some kind of insight. If it's getting found. Oh, this is what is killing us. If current I, well, current I does not equal start. Oh, you know what? Okay, so this is not updating current. Wait, here. Current IJ, this is gonna get us our came from. This needs to be current. And this needs to be this. Okay, so we add current. Update current to the next value. Yeah, okay. Like I said, while loops. I just forgot about this while loop. Oh, that's so sad. Okay, cool. I really hope that did it. And click. Oh, wait. Gotta play. Click. Hey! And it did the fill everything in black. That's pretty funny. Well, now we can tell where it was searched, which is kind of cool. First, I'm going to go through and get rid of all of these prints because we don't need these anymore. Our algorithm worked, which is what's nice about taking an algorithm that somebody already built and just implementing it. And we can get rid of that. And we can get rid of this and that. Okay, great. Now let's hit play. Boom, boom. Let's click here. Can't go. Oh, we got this came from garbage. Let's get rid of this. I want to be able to see what's going on. Also, let's get rid of this set color thing. No. What? Set color? No. Huh? Where did we? Oh, that was in our map. Actually, I don't want to do that just yet. I want to keep it because, hey, look, we can go here, here, and check everything. Now, if I click here, though, could not find path to location. It's interesting. Yeah, it didn't even have to check these because they're not going to get it to the location. Very interesting. Okay, let's go back to the build. And let's make a grove of trees around here. Now let's go play it. Oh, can't go there. Could not find a path. Not even gonna bother. Ooh, that was interesting. Ah, this is cool. Here, we're gonna do this. We're gonna put our player down here. Now what we're gonna do is hit play. Let's try to go here. Now look at that. Could not path to location. Now why couldn't it path to that location, you ask? Well, because we had our extra safeguard here of only checking 100 times, and that location is not within 100 times. So let's get rid of our run times. We don't need that anymore now that we've figured out which was the offending while loop. And so now, if we put our player down here, we hit play, let's go here. Hey, look, he made it. Also, this is going to make more sense. If I go here and I try to go here, it still also checks all the locations. Yeah, the whole reason it was like not checking locations up here is just because it hit the end of its possible loop. Okay, great. So now we can get rid of that, and that's just in time. Okay, so I'm about to end this. As always, you're going to be able to find this code up on GitHub. And where the heck is this? And you can see these videos on YouTube. You can find them easy. Like the easiest way to find them is through TylerMakes.com. We can just get rid of this set color. Might want to add that back later for some cool stuff, but not just yet. Now we can just go around and hey, look, our player can go wherever we want him to go. Isn't that special? Ah, it's so much fun. I don't even care if the path is not like a pretty path. It's a path, and that is excellent. That is so cool. Okay, awesome. So yeah, go to TylerMakes.com. Check it out. If you're watching this on YouTube, like, subscribe, etc. If you're watching it on Twitch, also like, subscribe, etc. Here it is. Yeah, you can go to TylerMakes.com. And you can find my YouTube channel where you can find all these videos. You can also get links from the video to GitHub where you can get the code. All right. Thank you very much, and see you next week. Bye.